Top of the morning to you. My name is Seamus Michael O'Flanagan, and I'll be teaching you for today. Your regular teacher's taking the day off. Today we're going to be covering secants and tangents, and this is 10.4 in your books, if you want to follow along. Your objectives for today: you're going to be able to identify secant and tangent lines. You're going to be able to identify secant and tangent segments. And you're going to be able to distinguish between two types of tangent circles. And then you're going to be able to recognize common internal and common external tangents. Let's start with some definitions, shall we? A secant is a line that intersects a circle at exactly 2 points. A tangent is a line that intersects a circle at exactly 1 point and is called the point of tangency or the point of contact. So a secant, here we've got the line touches at 2 points, so that would make it a secant. We've got here one that touches at 1 point, so that would be a tangent line. And this point right here is called the point of tangency. Tangency, or the point of contact. Just so you know, in case you're told that something's a point of tangency or a point of contact, you know what it's in reference to. Alright, let's go on to some postulates. So, first postulate: a tangent line is perpendicular to the radius drawn to the point of contact. Another postulate: if a line is perpendicular to a radius at its outer endpoint, then it is tangent to the circle. So first line, a tangent line is perpendicular. Okay, we've got this tangent line touches once. Okay, if you draw a line from the tangent line to the radius, you're going to have a perpendicular line. And then the other postulate is basically the opposite of that. If a line is perpendicular to the radius at its outer endpoint, then it is tangent to the circle. Makes sense? I sure hope so. Okay, secant and tangent segments. Let's move on to those, shall we? A tangent segment is the part of a tangent line between the point of contact and a point outside the circle. So that would be this right here. The part of the tangent line. Okay, this would be the tangent segment. Right here. The secant segment is the part of the secant line that joins a point outside the circle to the farthest intersection point of the secant and the circle. Okay? And then one more, the external part. The part of the secant line that joins the outside point to the nearer intersection point. So the question here is, which is the external, which is the secant? Well, here's the secant segment right here. And here's the external part. I guess that part is important. Okay, moving right along, shall we? Oh, we've got a theorem. Theorem 85 states that if two tangent segments are drawn to a circle from an external point, then those segments are congruent, and this is called the two-tangent theorem. Two-tangent theorem. Okay, and we could prove this if we wanted by drawing a point. We've got the center of the circle there, and then remember what we know about circles and tangent lines and radii. They form perpendicular lines. We could say that radii of a circle are congruent. We could say this one's congruent by reflexive, and then we could prove that these two triangles were congruent by hypotenuse leg, and then we could say that these two were congruent by CPCTC. So that's basically a quick proof of this theorem, because you know how much your teacher likes you to do proofs of theorems. Alright, let's move along to tangent circles. Circles that intersect each other at exactly 1 point are tangent circles. Now, they intersect each other at exactly 1 point. Something to keep in mind, something that's very important. So there's an example of a tangent circle. These two circles touch, You've got your tangent line that runs between them to help illustrate that point. Okay, and these are externally tangent circles. Circles that intersect each other at exactly one point outside of each other. Here, again, only one point. Only one point that they are touching. Okay, that they are intersecting. However, one's inside the other now. So what do you think that one's called? Ah, boy-o. Or girl-o, I suppose. This would be an internally tangent circle. And these are circles that intersect each other at exactly one point inside the other. Okay, so that makes sense hopefully as well. Alright, now, some common tangents. Whoa, look at this mess. Okay, so we would say that PQ is the line of centers. PQ is, incidentally, the first and middle initial of your teacher, if you didn't know that already. So PQ is the line of centers. It connects the two centers of the two circles. XY, okay, is a common internal tangent. Internal because it goes in between the two circles. Next, AB is a common external tangent because it runs the outside of the circles and it's a tangent line to both of them. Alright, enough of the nonsense. Let's try a practice problem. So we've got segment BA and segment BC are tangent segments, and BC equals 2x plus 3. So we'll say 2x plus 3. AB is 7x minus 22. And OA is 3x minus 7. And we want to find the length of the diameter of circle O. Well, let's start with this. We know that these two lines are tangent segments because we're told that. So we can set them equal to each other. So we can say 2x plus 3 equals 7x minus 22. You're taking your combine your like terms, which when you do that, you get 25 equals 5x. And we'll leave you with x equals 5 once you divide the 5 off. However, all that does is tell you what x is. It doesn't tell you anything else. Okay, you take that, and we know that segment OA is 3x minus 7. So we take the 5, plug it in for the x. 3 times 5 is 15, minus 7 is 8. But again, that doesn't answer the question. You've got to make sure to read the problems carefully. Because segment OA is just the radius. We want to know the length of the diameter. So we take that and we multiply it by 2 to get the diameter is 16. So be very, very careful, please. I'm begging you. Now let's try another practice problem. Something a little bit more difficult. So we've got a circle with a radius of 8 centimeters that is externally tangent to a circle with a radius of 18 centimeters. We need to find the lengths of the common external tangent. So that's basically we're trying to find AB. So what you do is you say, well, I know that this part here is 8. I know that this one's 18, but if I draw a line straight over, I can split that up. And then I can draw the line of centers in as well. And I can split that 18 up and I can say, oh, now it's 10 and 8. Because remember, if I draw a right angle here, this is a right angle because it's coming from the radius. And we know that this is a right angle because it's coming from the radius. So if I draw a line that forms two right angles, that'll give you, you can say that this is 8 and this is 8 because we've got a rectangle here, which will leave you with 10 here. Okay? So that's how you set that one up. And then you can say that, well, I know that this part here is 18 and this part here is 8 because these are also radii of these circles. So we can find the length of this. We take the 8 plus the 18, which gives us the 26. So I know that this part here is a radii of this circle, which we set up here, was 18. Same with this. So we know that that part is 26 squared. This is 10 squared. Plus RP squared. How's that going to help us, I wonder? So when you do all the math and you figure it out, you get that RP is plus or minus 24. Well, obviously, we throw out the negative 24 because we can't have a measurement that's negative. Therefore, AB has to equal 24. Now, why is that? Because if this segment here is 24, remember we said that this was a rectangle. So AB also has to be 24.